But before we, yes?
What's trigonometry?
We're going to tell you that. Okay? It's those wiggly curves. Okay, and understanding one. Before I do that, there are some people with less algebra background than others, and I'm going to start by simply talking about a little bit of algebra stuff just to make sure everybody has an equal background. Forgot to try pens, so we'll see what pens. That's a good pen. Okay, so how many of you have graph functions? I'm
Well,
looking.
I think.
Okay. Oh, I have to keep moving my mouse. Oh, it went to screensaver. Okay, we'll leave it alone for now. Okay, if you have a function, that's a formula, y equals x squared. You can make a table. And so if x is 1, what's its square?
1.
Good. If x is 2, what's y?
4.
If x is minus 2, what is y?
4.
These are hard, right?
Right.
3
9.
and minus 3.
9.
Okay, and then you plot these things in the xy plane. So 1, 1 is there. I didn't write it. Minus 1, 1 is there. 2 gives me a 4. 3 gives me a 9. Back down here, minus 1, minus 2, minus 3 gives me a nice symmetric picture. And then if you have a number like a half, 1/2, what's the square of a half? 1/4. And so you get a point there and a point there, and then you do all these dots in between, and you put them together, and you have a graph, and that's called a parabola, that shape. And so we're going to be graphing functions, okay? And a formula like that is called a function. You put in a number, it gives back an answer, okay? Okay, and since I've never done this class before at this age group, I'm going to be fumbling around. So I'm trying to figure out what to talk about next. I think the first thing I should talk about is angles and angular measure. So when we're in the xy plane, sort of the space between two rays is called an angle. And typically in the xy plane, there's x, there's y. We measure angles from the positive x-axis. And so that's called a positive angle. And that might be like 60 degrees, right? Everybody understand that? Anybody not done that before? Okay, and now this one, the mirror image down here, which goes that way, what's it called?
-60.
-60. Okay, or it can be called 300 degrees. Either way, both are acceptable. Or it can be called 660. You go around 360 and then another 300. So that's also 665 degrees. Okay? Okay, now did everybody here do CMath with me?
Oh, yes.
Yes. This is good.
This
This is
kid
all
did it.
CMath.
I did.
So when we did that,
This
you
kid
learned
did it.
about radian measure. In your school, did you do radians?
No.
Anybody do radians in school?
I know.
Okay, so should I have you all stand up again? Like you did at CMath? Or just tell you? Just tell you. Okay, when I turn like this, that's turning by pi. When I turn like this, that's turning by minus pi. And so this angle there is pi. This turn that way is minus pi. So 60 is 1/3 of 180. So this is pi over 3. This one here is minus pi over 3. Okay? Yes?
Then what's one right there?
Here?
No.
Here?
What's from the center, bottom left, like the
Bottom.
opposite? Yeah, that.
Here? That would be minus 2 pi over 3 if I think about coming this way, or it is pi plus pi over 3, which is 4 pi over 3. Pi plus another pi over 3, okay, is pi plus pi over 3 is 1 plus a third pi's, which is 4/3 pi. Okay? And don't hesitate to slow me down if I say anything that's confusing. Okay? I want you to understand. Yes.
So an angle of 120 degrees in radians would be 2 pi divided by 3?
Correct. Exactly. Okay. And so that's angles. And we measure them from the positive x-axis. Unless we have two rays, and then we can measure the angle between the two. Okay? But if you're just given one ray, then it's measured from the positive x-axis. By the way, I have notes, and I'm going to print them up and give them to you after I discuss them. There are things in here about proofs that I don't want you to read it before coming to class, because I want you to think about how you would do it yourself. So I don't want to give it to you in advance. Okay, we just finished 3 pages. Now we have parts of a circle. Here's the next thing in there. This is called the complex circles class. And that's because we're going to study complex numbers, and there is a circle, very important circle, when you discuss complex numbers, and it's called the unit complex circle. So this is the complex circle. Okay, following on the terminology of math circles. Okay, here is a circle. Okay? And there are lines. I can draw a line all the way across. What is that called?
Diameter.
Okay. So the line is called a diameter, and its length is called the diameter of the circle. Okay? What is that line called?
Radius.
Radius. So it can be called, the line can be called a radius, or the length of the line can be called the radius of the circle. Okay? The edge, what is that called?
Circumference.
Here it is. Good. Okay, thank you. Thank you. Okay, so that's the circle, the circumference. Now there's a couple other lines and things that we can talk about. If I have a line that cuts across it like that.
Chord.
Chord. Thank you. Who has never heard that word before? Okay, now you hear it. Okay? That's a chord. And it cuts off a piece of the circle. Hello. The projector. I fixed it.
Okay, sweet.
I went to the settings and found the colors and turned the blue off and then turned it back on, and it fixed itself.
Oh, okay.
Thank
It
you.
would probably actually the cables if it was changing colors.
Maybe.
So,
Thank you. Okay, you draw radial lines out, and this part here, that portion of the circle, anybody know what that's called? Sector of the circle. S-E-C-T-O-R. And this piece of the circumference, does anybody know what that is called?
Arc.
An arc. And the chord, the sector, and the arc are subtended
Oh, I see.
by the angle theta. So this is the angle theta, or it's subtended by these two rays. It's the part that's cut out by those rays, and the fancy word is it's subtended. Don't know where that word comes from, and I don't know what supertended is. This is subtended. Arc sector, radial lines, and then you have the area, which is everything inside, and the sector, which is a piece of what's inside. And now we need to know the formulas for computing these various things. Yep.
What's the importance of theta?
It's a
It's
variable.
the
It's just the letter of the alphabet, Greek alphabet that we use to describe the angle.
What exactly is it? Like,
It's a variable.
Theta?
yeah,
Just a
what's
variable.
this number equivalent? Like pi?
No,
It's
it's
the
not
same thing as
anything. It could be
X.
anything.
Yeah.
It could say X, could be 1, it could be negative 5, it could be pi.
Okay, it's a symbol standing for some angle where I'm not going to specify what angle it is. Okay? Okay, now, what's the formula for the circumference in terms of the diameter? Pi times the diameter. Or, what is it in terms of the radius? And there is a movement afoot to replace the letter pi by a new letter called tau.
Oh, I know what that is. That's 2 pi.
Tau, and I won't use it, is 2 pi. And so the formula is tau r.
Why would they do that?
2 pi r is the yeah, but every time you use pi, then you have to.
I do not expect it to catch on, but there is the tau movement, which is trying to replace pi, and there's so much written in terms of pi. It just changes all the formulas by factors of 2 floating around in different places, just to confuse you no end. Okay? So now
Zero trigonometry
I
wasn't
told
hard
you about
enough.
tau. You can look up tau in Wikipedia and find out about what all the changes are in the various
Made it
formulas.
up.
Don't
Actually, a friend of mine wrote a paper on it. Bob Palais. I have no idea if he was the first one to use it or not. Anyway, there's the circumference. What about the area of the circle? Pi r squared. And what is it in terms of the diameter?
Oh,
That's the same
pi
as tau,
times
then
theta,
you have
which is
tau
squared.
over 2.
Pi d squared over 2. 4, not 2, 4.
That's my goal.
Because you got to square the r
Yeah,
is d over 2, and you square it, you get a 4 in the bottom. Right? And now what would this be in terms of tau? This would be 1/2 tau r squared, and this would be 1/8
Is it okay if we
Please
don't use
don't.
tau?
Please don't.
squared.
See, that's
Can we not use tau?
Don't use tau.
Tau is
Yay.
No one in the world uses it. That's not true. There's about 10 people out of the billions in the world who use tau. So, okay. There's the area. And now, suppose, what is the angle all the way around?
360.
360. And so here we have a sector of the circle subtending an arc. How long is the arc if the angle is theta degrees? So if theta in degrees, okay, theta is given in degrees, what fraction of the whole circle is in this sector? The fraction is theta over 360. I heard somebody say that one. Yes, Parth. Okay. And so, what is the length of the arc? The whole circumference is 2 pi r. What's the length of this arc with the angle theta?
Fraction.
What fraction of the whole circle is in this part? 360 degrees is the whole thing, and theta degrees is this part. So the fraction of the whole circle is theta over 360, right? If theta was 45 degrees, it would be 45 over 360 to get the fraction. Yep.
Then how do you find the length of the arc?
Well, it's this fraction of the full circumference.
So you're finding the degree?
You know, you're
No,
finding,
you
you're
multiply
finding the
the-
fraction of theta, finding what part of theta is turned
So
whole
the
circle.
arc is 2
Is it
pi
1/2
r,
before?
and then we multiply it by the fraction theta over 360,
Oh.
right? And that's the length of the arc. Okay? Now, if we do theta in degrees, no, I'm sorry, in radians, okay, then the fraction is, what's the fraction now?
Theta over 2 pi.
Theta over 2 pi.
What is that?
And the arc then becomes theta over 2 pi times 2 pi r, which is just theta times r.
I'm
Ah.
so confused
Oh
right
my
now.
god. No, because 2 pi cancels out, so you just have theta r.
Okay, what are you
equals
confused
to
about?
180 degrees.
I don't know where you got all.
Why do you go back to pi?
Theta.
The
over-
fraction, the whole way around is 360.
Yes,
We're only going theta around.
yes,
So theta over 360 is the fraction of the way around.
yes.
That fraction of the full circumference is the piece of the circumference between here and here. Then 2 pi r is the length all the way around. I only want this fraction of that.
Okay.
So if theta were 90 degrees, this would be 1/4 of the way around. We get 1/4 of the circumference.
Why?
R is the circumference.
Oh!
Oh,
How'd you get it to 2 pi? Theta over 2 pi.
Okay? If the theta
Oh,
is
in
measured in
radians.
radians
Ah.
instead of degrees, then theta over 2 pi will be the fraction instead of theta over 360.
So,
Why is it?
by
Yes?
like,
One second. What?
So why is it theta over 2 pi?
2 pi is the angle going all the way around. Theta in radians is this much.
So,
This much over 2 pi to go all the way around is the fraction of the circle that's in this angle.
so 360 degrees
Is
equals
2 pi.
pi radians.
2 pi radians,
okay, so,
right?
in order, so, finally
Is this
the arc.
obvious? Is this all obvious to you? Yeah.
So, hold on.
You've had it.
Wait.
We're
So,
catching
finally
deep
the
water.
arc, you just need to use the equation theta over 2 pi.
It's that fraction of
Okay.
the circumference, right? And so using this as the fraction instead of theta over 360, now there's it multiplied by 2 pi and divided by 2 pi. They cancel, leaving you with theta times r.
Oh, so it's just beta times r?
Right, which is a really simple formula for the arc,
I get it now.
right?
Oh.
And that's one of the reasons why mathematicians like to use radian measure.
That was in this book.
Okay, r means
That's right.
radius,
Oh my
right?
god, I had that.
Yeah, okay, radians. Or a v means radians.
Okay? All right, what about the sector? The sector is the part of the area. If you use degrees, then the sector has area theta over 360 times pi r squared. Okay?
That's
If we use radians, then we replace this pi theta over 2 pi, theta over 2 pi times pi r squared, and we get 1/2 theta r squared for the area of the sector.
Wait.
And these formulas here for the arc length and the sector area are so much simpler than these formulas. That is why we use radian measures.
So the sector
The area of the sector.
is half beta times r squared.
Yes, if theta is measured in radians.
Okay.
Okay? And so if it's 90 degrees, that's pi over 2 radians. The area will be 1/2 of pi over 2 times r squared.
Okay.
Okay?
Okay. What's the difference between radians and, what's the other one?
Degrees.
What's the difference between the two?
How we say how big an angle is.
Radians is in terms of pi.
Oh, that whole
Degree-
pi,
well, degree-
negative pi, I get it.
And
I get it.
degrees
I
is
get it.
like-
I get it.
Okay? So, this is 45 degrees, but it is also pi over 4 radians. Right? And so, if you use 45 degrees, you got to use this formula for the length of an arc. If you use pi over 4 radians, you have to use this formula for the length of the arc. And this formula is so much easier, it's much nicer to use radians to describe it. Okay? Okay. That's why we use radians. And most of the time in math, we end up using radians instead of degrees. Okay, now we're coming to definitions of the trig function. So, let's see, I'll go down with that one. First, we're going to start with the triangle.
Just explain.
That's not pen. No. Where did I put down?
You are really particular about your pen.
I am, yes. Yeah. There's a good one. Okay, so there's our triangle. And we're thinking about this angle here called theta. Okay? And there are three, it's a right triangle. And we have three sides, A, B, and C. Okay? And I use those letters because A is sometimes called the altitude, B is called the base, and C is the hypotenuse. So, sorry about that. But A and B make sense when I do it that way. Okay? This side is called the opposite side, opposite to the angle theta. This side is next to it is called the adjacent, A, B, J, A, C, E, and T. And this one is the hypotenuse.
Wait.
Hypotenuse. Hypotenuse. Okay.
A calls the opposite.
So it's opposite to the angle I'm thinking. Talk, study.
Oh.
Okay? All right. So, in terms of those three sides, we define certain functions of this angle. And the first one is called the sine of theta. The second one is called the cosine of theta. The third is the tangent of theta. And there's three more, but we'll start with these three.
Yeah,
And
there's the cotangent.
the sine is A divided by C. The cosine is B divided by C. The tangent is A divided by B. Okay? And now, this is sometimes said to be opposite over hypotenuse. This is adjacent over hypotenuse. This is opposite over adjacent.
Oh, I found it. Sine?
And there's an acronym. Who knows what the word acronym means? What's an acronym?
Something you use to help math.
Right. Okay. And sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. Anybody pronounce that? Sakatoa. Okay. Which I always think of as
He
Sakatuum.
doesn't paint.
But it can also be think of as an Indian, American Indian, Native American name. Okay? But Anyway, that's how people remember the three formulas. Okay? Yes.
So these are always to get theta?
In terms of whenever, no matter what you pick for theta, as you open theta up, the A, B, and C will change, and you do these ratios, and you get a function of theta. Okay? Now, what happens if you have...
I
Pardon
don't
me?
quite get it.
Let's look at a concrete example. Okay? This triangle is a 30, 60, 90 degree triangle. Okay? And if this side is 1 and this side is the square root of 3, what does Pythagoras say about the third side? Do you know the Pythagoras theorem?
Yeah.
What does it say?
A squared plus B squared plus C squared.
A squared plus B squared equals C squared. So this is C. A is 1. B is the square root of 3. So what's C squared? C is 2.
Oh, C is
squared is
C is 2, right?
Yeah.
So that side is 2. And this is, it's called the 30, 60, 90 triangle. You remember it is 1, 2 square root of 3 for its sides. It's just something to be memorized. And we can now write down the sine of 30 degrees, the cosine of 30 degrees, the tangent of 30 degrees. What are they?
Okay. A
Opposite
over C,
over hypotenuse,
A over C,
which is,
1 over 2.
okay, what's the cosine?
Make the square root of 3 over 2.
And the
And
tangent?
then 1 over square root of 3.
Okay? Any questions about that? All right. Now, you can have more than one triangle which has a 30-degree angle. Let me draw you another one. This time it is 2 and 2 the square root of 3. I just doubled both of those sides. What happens to this side? Which is 4. They are similar triangles. This is still a 30-degree angle. So now we have to figure out the sine, cosine, and tangent of 30 degrees using these triangles. Okay? So, Rachel, tell them to me. Opposite over hypotenuse.
1 over 4, 2 over 3 over 4,
2 the square root of 3 over 4.
and then opposite over adjacent, square, 2 over 2 square.
And now these simplify. What cancels? What does it become? 1 half.
1 over 3. Square root.
1 over. Okay? And notice those are the same as here. Okay? So the sine, cosine, and tangent of 30 degrees is the same. If you have similar triangles, you can enlarge it however much you want, and it's still going to be the same. It only depends on what the angle is, not how big it is. Okay? Yes, Paul?
Can I sharpen my pencil?
Hmm?
Can I sharpen my pencil?
I don't have a sharpener here, so I simply give you another. You want to pick the eraser.
Yes.
Okay. So it doesn't matter how large it is, it just depends on the angle. Okay? Now, we can prove that. Yes?
So they're all those equations, the sin, cos, and tan, are all supposed
I'm close.
It's
Are
okay.
all
You can
supposed
say
to-
what you want.
to equal up to beta.
No, they're all functions of theta. Given an angle theta, we can find the sine, the cosine, and the tangent of that angle by drawing any triangle which has that angle on one of the corners and make it a right triangle, and then look at the other three sides, and you'll be able to figure out the sine, cosine, and tangent of 30 degrees. And we can do that for any angle theta. Okay?
Okay. And theta can be any angle.
Yes, I just did it as an example with theta. Okay? We can do it with 60 instead of 30. If we do it with 60, erase these, make it 60 instead of 30. Okay? Luke,
Okay.
what is the sine of 60? There's 60. Which side is opposite?
Square root 3.
So what is the sine of 60? Opposite over hypotenuse.
Square root 30.
Hypotenuse is the 1 now.
No, 60 degrees is the right triangle. The opposite, hypotenuse is always opposite right angle.
Oh, so 2. So it's the square root of 3 over 2.
Okay?
Okay, then it's 1 over 2.
Yes?
And then it's 2 opposite. Square root of 3 over 1.
Mm-hmm.
Okay. So this equals square root of 3 cut.
All right, so you should know the 30, 60, 90 triangle by heart, and you should also know the 45-degree right triangle by heart. Get rid of this. Here is a 45, 45, 90. Okay? 1, 1.
Square root 2.
What's the third side?
Square root.
Square root of 2. Any questions about that? Okay, so we can get the sine, the cosine, and the tangent of 45 degrees. The sine of this 45 is 1 over square root of 2, 1 over the square root of 2, and 1. Okay? Everybody got that? Okay. All right. So those are the triangle definitions. Now that only works if theta is what's called an acute angle, less than 90 degrees. Okay? This angle in here is acute, AC. Oops, I can't write what I'm saying. Acute, A-C-U-T-E. It's very pretty, so it's acute angle. It's less than 90 degrees, and so we can do angles that are less than 90 degrees, but we can't do angles bigger than 90 degrees this way. And so we want to give a definition that works when the angles are bigger than 90 degrees. That takes us to defining them in terms of circles instead of triangles. Oh, I should have said, what I wrote over here was in terms of degrees. You can also write this as sine of pi over 4 if you're talking about radians. Okay? Two of them going around. It's okay. I don't mind. Okay. All right. So now we're going to do a circle definition. Takes me to my next page. Circle definition. There's where I put down that good purple pen. Okay. Here is a circle again. Here are the x and y axes. Oh, yeah, that's okay. And the radius of the circle is r, and it has an x coordinate and a y coordinate. This point is xy. And for that angle right here, which I will call theta again. By the way, which Greek letters do you know? Read these off.
Alpha, beta,
Gamma, delta, epsilon, epsilon.
Oh,
Theta.
Eta.
But it's a semicolon, not theta.
Not theta. That one's phi.
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 Okay.
Kappa. Lambda.
Focus, upside down Y.
Okay. Now we come to Hebrew letters. What letter is that?
Oh, I know that.
Oh,
That.
You're right now.
Oh, I wish they
Which way is it? This way? No, that's backwards, isn't it?
I think so.
Anyone who wish here.
Gimel. Dalet is, what,
What?
looks
That's dull.
a little like that one, doesn't it?
Yeah.
No, it doesn't. It looks like it's that, that's Dalet. A.
Oh, what's that one? Gimel.
Anyway, the only one used in math is this. Aleph stands for
So if you
infinity.
said GP in English,
That's not
you'd
phrase.
be Eta Pi.
No, that's not a G.
Oh, what is that?
That's like C, but there's a Gimel. No, that's this one. That's G.
What Eta?
Eta, it sounds like, is like an H.
Oh, so.
Like the letter H. Anyway, so we don't use any more of the Hebrew letters. We only use, but we use most of the Greek letters. So we're going to be using some Greek letters here. Okay, here's a circle. In there, I just drew a right triangle. In terms of that right triangle, we have sine, cosine, and tangent of the angle theta. Okay, and so I need names. Anastasia, what's the sign for this triangle in terms of the letters X, Y, and R?
Y over R.
Y over R. Does everybody understand where we got that?
Yes.
Opposite over hypotenuse. Anastasia, go ahead.
X over R. And Y over X.
Okay, so there are the three basic trig functions, okay, for written in terms of a triangle drawn inside the circle. But now these formulas work even if the angle is bigger than 90 degrees. So I come over here and move my circle line to over here now, my radius. There's my angle theta. And this is now my point x, y. Which one of x or y is negative?
Y.
Y.
X.
X. Y. X.
Y.
X.
Y.
Y.
Because on the coordinate grid, here's all the positive numbers, it's over one.
Y's up here.
No, it's X.
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 X is negative.
Yes.
Okay, that's what everybody else said.
My bad.
Okay. So x is negative and y is positive. But we still use the same definitions. The sine of the angle comes out positive because y and r are positive. But the cosine of the angle comes out negative. And the tangent of the angle comes out negative because the x coordinate is now negative. Okay? And so we get both positive and negative angles. And so let's look at a concrete one. Here is my circle. Let's look at this angle, which is 135 degrees.
What would be the line of y for the top circle?
Say it again.
What would the line y be for the top circle?
Y equals x? What y? Which y are you talking about?
Because so this is no longer referring to a triangle.
There is sort of a right triangle over here.
Because sine and tangent sine refers to y
Right, over there, they were only defined for an angle inside of a triangle. If
Yes.
we open this side up beyond 90 degrees, it no longer forms this right triangle, it sort of forms a right triangle on the opposite side.
But for that one, the sign of that circle is still y over r.
Correct.
So where's the y?
For this point, it is that height. And for this point, it is the x-coordinate of that point. So here's the angle. It determines the ray off in this direction. Okay? Yeah?
If sine, cosine, and tangent are relations between the sides of the triangle.
They're no longer just relations between the sides of the triangle. They are relationships between the coordinates of a point on a circle and the radius of the circle. We throw away the triangle. The triangle only works up here when the point on the circle is in the first quadrant, the first quarter of the circle. Okay? Once you get beyond, in any of the other 3/4, it no longer is a triangle. It's a circle instead. And so it's a relationship between the coordinates of a point on the circle and the radius of the circle. And which point is specified by the angle. Okay?
Oh.
Okay. And so we throw away the triangle. Sometimes it's useful to think about it because now we want to figure out what are the coordinates of this point. This is at 135 degrees. How much is this angle?
45. Oh, 45.
45 degrees. Okay? So I drop a perpendicular. What's that angle?
45.
What's this angle?
45.
And it's a right triangle. And so if the radius is, if this line is 1, minus 1, and this is 1, then this diagonal, the radius of the circle will be square root of 2, okay? And we can write down the sine, cosine, and tangent of 135 degrees. Okay? And, okay, so, who hasn't helped? Who would like to help? Andy. Andy would like to help. Okay, so what is the sine of 135? Sine is the y coordinate over r. So what is the y coordinate of this point?
1 over square root of 2.
1 over the square root of 2. And the x coordinate is?
Negative 1 over square
So
root.
this cosine is negative 1 over square root of 2. And the tangent?
Negative 1.
Negative 1. Negative 1. 1 over negative 1 would be negative 1. Everybody got that?
I think so.
And now I'm ready to turn on the projector again. Save this pen. And it probably went to screensaver. There we are. Okay. And now I have to get the projector going again. You, where are you? There you are.
No, I didn't. I mean, I didn't really try out the water thing was so glaring. Like,
Is it coming on? Yeah, I have to.
I know, I know.
Tony, is that what level?
yeah.
I already got to say.
Coming out there? Don't see it. There it is. Now it's coming out.
Wait, what?
I'm sorry.
There we go. All right. Now, here is a circle. Here is a ray gradually going around. And theta is the angle between the x-axis and the ray. Okay? Now, I made the circle be radius 1. Okay? So that means when you have y over r, that's just y. When you have x over r, that's just x.
Let me guess, you made this.
Oh, I did. Exactly.
What's with the
This is
smiley
just
face?
like you learned in CMAP. I made all the pictures, and then I put them all together in a movie. Okay?
What's with the smiley face?
It's telling you if you want to look at the cosine picture, you got to turn your head on the side. Okay? And so that's graphing the cosine. And so now, watch this one. We're watching the y coordinate. When the angle was 0, let me start at 0. When the angle was 0, the height was 0. The angle is getting bigger, the angle gets to 1, comes back down to 0, goes down to -1, goes up to 0, and starts over. Okay? And so, as you go around, you watch the y coordinate. On a circle of radius 1, the y coordinate is sine of theta, and the x coordinate is cosine of theta. So here's the x coordinate, positive, negative, still negative, and now positive. Positive, negative, negative, now positive, and then it starts over again. Okay? And so this is how you get the graphs of sine of theta and cosine of theta. Any questions about that? They're very pretty graphs, and you can get it by looking sideways.
Oh, come on, that's a 24-hour clock.
Cosine. Okay?
Whatever.
Well, I just put a 24-hour clock. I can't.
So
It's the Unix system that I don't set it. Yes,
So for
Well, I'm
cosine
too
of
lazy.
theta is the
x coordinate in the circle. It's the circle of radius 1. And it doesn't matter how big you make your circle or smaller, just like over here, I could double the size of all the sides and the ratios would still stay the same, okay? Or triple the size. Likewise, I can change the ratio, and when I do the drawing of the curve, it'll just get bigger. It won't go from -1 to 1 anymore. It'll go from -r to r, but it'll still wiggle in the same sine curve pattern, up and down. Yeah.
so for sine when the theta represents the angle
Right.
relative to the x-axis,
Correct.
and for so
Cosine also relative to the x-axis.
Why just copyright this?
I always copyright everything
I was like,
because I want to use it in a book eventually.
okay.
Oh.
At
But
one
it's
point,
only
or
for
another.
this year.
2007 to 2013.
I know.
Well,
It's 2013.
in 2007, Amy Sue was a student in my honors calculus class, and she needed to do a Maple project, and I said, this would be a good Maple project, is to make this computer animation. And so she did what you did in middle school as her project for the honors calculus class.
What did we do?
Okay, but she didn't just do this one. Let me scroll down and show you the next one that she
Wait,
did.
how come they say copyrighted by you?
Huh?
Like, how come they say copyrighted by you? They should say.
Because anybody in my honors classes turns their ownership over to me, and if it's published, they will get a reference, a citation in there, just like this. Every time somebody reads it, they will see it. But if I'm going to make a profit on it, they have to turn it over to me, and I copyright it. Here is the second one.
Oh, it's
My
This
God.
draws tangents and cotangents.
Oh my gosh, too confusing.
And this is the graph of the tangent of the angle, the y over x. And one of the questions I would like this class to figure out is, why does that picture give the tangent over here? Because it looks cool, okay. That's not a proof.
Are you seriously
Okay,
like
in other words, y is the height on this graph, the y divided by x of the point on the circle.
Because it was
The tangent is defined to be y over x. Y is the height of this, and I can't stop these. That's something else I want to do, is make it so that I can have a button to pause it. Okay, and I haven't done that yet. This class may do it, somebody here, yes?
Since the radius is 1, the sine
That's of the point on the circle there, is the y and the x we're talking about.
Right.
Okay? And now you have to figure out why. You'll notice this horizontal line, which is drawing it, is the height on this vertical tangent to the circle at the edge. Okay? And so the question is, why does the line on where the radial line extends and hits that vertical tangent, why is that height tangent of theta? Okay, why is it? Yes?
After it passes, I can't exactly.
Really great.
After it passes a certain point,
There you go. Great job.
like the proportion.
Let me draw the circles as a still picture so it doesn't keep moving with us.
You go down.
And the answer is it has to do with similar triangles. So you got to find the right similar triangles to explain why this works. Okay, so here is our circle. Here are some axes. Here is the tangent line at the x-axis. Okay, here is an angle coming out. So that's the angle theta. The circle is radius 1. Okay, and this point is x comma y. And I claim, and you need to prove, show, this is THIS, there's the I, is tangent of theta, which is y divided by x. Why is this height equal to the y coordinate here divided by the x coordinate? So let's call that height h. Okay? And you're trying to find a reason why h is tangent of theta. Yes, Clark?
Because, what are you
Here
saying?
you are. Come on up.
Well, if are you saying, asking me to point out the two similar?
Sure.
This one,
And what are the lengths of the sides? This point is xy. What's this side down here? What does it mean to say the coordinates of that point are xy? What does it say about this length?
that's it.
Write them in.
Oh, that's what you meant.
So that's x, and that's y. So, and this hypotenuse is what length? What's the radius of the circle? That one in. Okay? And now, this length is, and this length is h. And so what's the ratios that tell you what h is from the similar triangles? H over 1, write that down, h over 1 equals, and what's another name for y over x? And you just proved that the h over 1, which means h, is tangent of theta. Right? Did everybody follow that?
Yes,
Not there. Okay, here we have a triangle whose sides are x, y, and 1. Here we have a triangle whose sides are 1, h, and something. Okay? And they are similar triangles because they've got the same angle theta here, and they are both right angles there. So those are similar triangles. Okay? And when you have similar triangles, ratios of sides are equal. And so h over 1, the two legs of the big triangle, is equal to y over x, the legs of the small triangle. Okay? That's why this is true. And then y over x is the definition of tangent of theta. Okay? Now, for some similar reasons, this one, turning your head sideways, is the cotangent of theta. Okay? So that's the next thing Amy did. And finally, secant and cosecant, we haven't defined them. So here are the formulas for sine, cosine, and tangent. Here's cotangent is B over A. Secant is C over B. And cosecant,
It's C over A.
yes, thank you, good guessing. C over A. They're just these ones upside down, okay? And so this is 1 divided by the sine of theta. This is 1 divided by the cosine of theta. This is 1 divided by the tangent of theta. Okay? And so when the cosine goes to 0, the secant goes to infinity. When the sine goes to 0, the secant goes to infinity. The cosecant goes to infinity. Okay? When the tangent goes to 0, the cotangent goes to infinity. When the cotangent goes to 0, the tangent goes to infinity. Okay? And so sine of 0 is 0. Cosine of 0 is 1. So here's secant. Cosine of 0 is 1. So secant of 0 is 1. Cosine of pi over 2, which is 90 degrees, is 0. So secant is infinity, or minus infinity. And so these are the graphs of the secant and the cosecant. And they are done by constructing the circle, putting out the ray at angle theta, doing the tangent line at that point, and seeing where it intersects the x and y axes. And those points on the x and y axes will be the secant and cosecant. Okay? Once again, that requires a proof. Okay? And we have 8 minutes. So can somebody suggest a proof? Again, similar triangles, something like this. I will draw it over here, but you think about it, and I can use a volunteer. Somebody like Parth, who did the first one, so it should be somebody else, to come up and explain why those come out to be. So I better write down what secant and cosecant are. Oh, they're there. They're right there. Okay? So I'm going to draw a still picture of it. And we have a ray here at an angle theta. We draw the tangent line there. And then this distance, so the radius is 1, r equals 1. And let's see, this distance here comes out to be secant, S-E-C, of theta. And this distance here is cosecant of theta. So this point here is x comma y, and we're trying to show that this is secant. Secant is 1 over x. And we're trying to show that this thing here is 1 over y. It's not easy. Think about it and see if you can find similar triangles to draw that will show that secant, that horizontal line there is 1 over x. Drawing one more line. This line here, this distance is x, this distance is y. So y is this distance, 1 over x. You want to come up and explain? There you go. Okay, well then tell me. You want me to do the writing?
Well, the tangent line and the radius are right.
They're perpendicular. Yes?
That makes another right triangle.
This is a right triangle and this is a right triangle. Yes?
There's also one for the cosecant sines.
Yes, we're trying, let's try to get this one. Okay, so let me enlarge the two triangles. X, Y, and an angle theta, and the hypotenuse is 1. The other one looks like this. This side is 1. This is X, and we're trying to show, so there's a right angle, there's a right angle, that's theta. And we would like to know what this side is. Okay, so, hello, that's Trevor.
Hi,
He's
Trevor.
joining us for the second half. Okay, so what over what is equal to what over what?
1 over x is
1 over x here is hypotenuse over adjacent. And so let me call this little a.
little a and little
So a is 1 over x. And 1 over x is the secant. Okay? So there we have our all these different pictures. Amy, I had drawn the sine and cosine one and animated them, and she came and animated the other two for me. Okay? And so that was a good job. That's why her name's on it. Okay? All right, so we have done trig functions, special angles, graphs using special angles, and so we'll continue from there next time on this. Am I correct? Everybody's going to the Maple? Is there anybody who's cutting out, leaving at 4? No. Okay, good. All right. If possible, there could be somebody in the class who only wants to come to the trig and complex numbers, but not the Maple part. I have counts for you. We will, oh, you can stop.